the last section, I introduced linear models considering the motion of the objects attached to the springs. Now also consider the oscillational motions, but in this case is a non-linear model. One of the examples of the non-linear model is a model of pendulums. So object is attached to the strings, and string is attached to the loop. The length of the string is L, lowercase of the L. And the object is oscillational motions under the gravities. And the angle formed by the vertical line with the strings is theta. The length of the object moving from the lowest part, this length is expressed L theta. This is the length of the S. If you consider a small change of the length ds, the length of the strings doesn't change, so ds is expressed L times the d theta. So this corresponds to this small change of the length. This is d theta, then this ds is expressed L d theta. Then velocity of our object is expressed as ds dt. This is a velocity. So if you divide it by dt in the both sides of the equation, this equation it becomes L d theta dt. If you want to find that acceleration, find the derivative of v with respect to t. So it becomes L second derivative of theta with respect to t. This is acceleration. Now we'd like to write the equation of motion. We need to consider the force acting on the object under the gravities. Then gravitational force and the tension force is acting on this object. But tension force is this direction. Tension force is always perpendicular to the motion of an object. So we'd like to consider the force acting on the object along the direction of the motion of our object. You should take into account the gravitational force. The only important component of the gravity is along the line of the motion of the object. So if you draw the triangles, these triangles, you can easily find that this theta is exactly equal to this theta. Then component of the gravities along the motion of the object is mg sine theta. So force acting on the object is expressed F equal minus mg sine theta. We'd like to write the equation of motion. Equation of motion is expressed ma equal F. So this is m, this is acceleration. And then you can substitute. The acceleration is L times the second derivative of theta with respect to t. This is acceleration. And this is force. So we have a ml second derivative of theta with respect to t equal minus mg sine theta. Now dependent variables is theta. Independent variables is t. This is second derivative equal minus g over L sine theta. So as I explained, sine theta can be expressed if you use a Taylor series expansion. This is theta minus 1 over factorial of 3 theta cube plus 1 over factorial of 5 theta to the 5 minus blah blah blah. So because of the existence of these terms, this is nonlinear terms. So because of the existence of these terms, this equation is a nonlinear differential equation. It's quite difficult to solve the nonlinear differential equation. So we'd like to simplify the equations using the linearizations. So in the linearization, among the many terms of the sine thetas, we just pick up only the biggest terms of the thetas. Then equation is simplified to becomes L second derivative of theta with respect to t is minus g thetas. So this equation is expressed second derivative of theta with respect to t minus G over L theta. This is a linear differential equation. We can easily solve this differential equation. The answer, general solution, is expressed. Theta is expressed capital A sine square root G over LT plus B cosine square root G over LT. Once you got a general solution, you might apply this equation even when the theta is a really big one. But you should not apply this equation to the motion of pendulums when the theta is a really big one, because to obtain this solution, we use this assumption. Theta have to be the really small numbers. So when you use linearization, always you have to keep in mind the assumptions you made. Okay, so this is the end of this session, and also this is the end of this chapter.